And I'm very pleased to say that we have Dr. Nick Bonne here to give us today's plenary talk on the Tactile Universe. Dr. Bonne got his PhD from Monash University in 2005, and he moved to the University of Portsmouth in 2015, and he moved to the University of Portsmouth in 2014, where he started as an Endeavour Fellow and then transitioned to a Public Engagement and Outreach Fellow at the Institute of Cosmology and Gravitation at the University of Portsmouth. So today, we're very lucky that he's going to be telling us all about the Tactile Universe project, which is a project that uses multisensory techniques for communicating ideas about current research in astrophysics. And now, while this project was aimed at helping blind and vision impaired people access astronomy, it's not just about helping one section of people. Improving accessibility helps everybody, and that's what is so important. So I'm going to hand it over to Nick now, and we're looking forward to your really exciting talk. Thank you.
Thank you so much, and good morning, everybody. And so, first of all, thank you so much to the NAM organisers and the University of Bath for the invitation to come and talk today. It's a real honour. So I'm going to be talking about the Tactile Universe project for the next 45 minutes or so. I thought before I started, I'd give you just a little bit of background on myself. So my PhD work was on galaxies research. I calculated luminosity functions of local universe galaxy populations. I also looked at a lot of the physical properties of these galaxies, so things like the galaxy morphologies, the galaxy colors. My real interest in all of this, though, in communicating astronomy in different ways, is that I'm actually somebody with a severe vision impairment. So I was born with my eye condition, but I've always been interested in space, and from a very young age, I knew that I wanted to be an astronomer. And it wasn't always particularly straightforward. There was lots of thinking outside the box, working out interesting ways to learn what I needed to learn to become an astronomer. So that's sort of where my stake in all of this comes from. Okay. So having said all of that, I think you'll all probably agree with me when I say that astronomy is a pretty visual science. So the way we talk about astronomy, the way we communicate astronomy to the public, the way we do our research, the way we collect our data, all of that is really, really visual. And the visual nature of the subject can make it very difficult for people with vision impairments to actually access the information that they need to work as astronomers or just to be interested in the subject of astronomy. Having said that, though, it's worth noting that a lot of the astronomy that we do is actually, it relies on augmented vision. So we have to use telescopes to see the fainter objects in the universe. We have to point those telescopes at those objects for hours and hours and hours to collect enough light to actually see these things. We use telescopes to look outside the visible spectrum. We use our computers to digitally enhance various aspects of images, to zoom, to change the contrast, to do all kinds of things to see our data better, to clean up noise, do all kinds of things like that. So much of the astronomy that we do actually doesn't use just our eyes the way that they are. So that's a really important thing to remember. Okay, so our solution to this issue of astronomy being so visual, of visually impaired people having trouble accessing it, is the Tactile Universe project. So this is an award-winning public engagement project, which we started back in 2016, which uses tactile representations of real data to make current topics in astrophysics research more accessible to the blind and vision impaired community. And the main goals of this project are as follows. What we really want to be able to do is show young people with vision impairments that STEM subjects, in particular astronomy, are subjects that they can do, that they can be interested in, that they can access. And by doing that, we want to raise the aspirations of these young people. And yeah, just give them the ability to access these subjects if they really want to. We want to do this by developing and sharing accessible resources, which can be used both for education and in some cases, hopefully for research as well. We also want to be able to help and inspire others in communicating their research and their science in more accessible ways. And so throughout this talk, I'm going to describe how we've been pursuing these three main goals over the last couple of years. Okay. Of course, before I go any further, I need to acknowledge that, of course, this project is a team effort. Here I've got all of the Portsmouth Tactile Universe team members, the people who are currently working on the project and who are based at Portsmouth. There's, of course, myself, so I'm project lead at the moment. We also have Jen Gupta, who is the Outreach and Public Engagement Manager at the ICG. So she's been, I guess, the brains behind a lot of our strategizing, a lot of the decisions we've made to get the project out to people effectively and to expand the project's reach. We also have Coleman Krozek, who's our technical lead. So Coleman is the one who came up with the methods that we've used to create our 3D models, our tactile images. Coleman's done a lot of work on the project as well. We currently also have Laura Nuttall, who's one of the ICG's gravitational wave researchers. So Laura is sort of our science lead on that aspect of the project. We also just recently have been getting the help of two PhD students who are also working on gravitational wave stuff. And so that's Simone and Connor. And I'll show you a little bit of their work at the very end of the presentation. Okay, so up on the screen here, I have an image of a galaxy. So this is the galaxy Messier 51. Those of you who can see your screens will be able to see that there's just a ridiculous amount of detail in this image. And just looking at this conveys so much information. We can see the various features of this galaxy. We can see that it has a central bulge, that it has these spiral arms that wind out. We can sort of see the feathering almost of the gas and the dust that make up these arms as they wind out from the center. We can see the small companion galaxy off to the side in the top right-hand corner of the image that's having its material stripped away by the gravity of this much larger central galaxy. So there's all of this stuff that we can pick up with just our eyes by looking at this image. The problem is, though, how do we convey all of this information to somebody who can't see this image, who can't see all of this striking detail? And that was the initial sort of question that we wanted to try and answer with the Tactile Universe. And we came up with a really simple solution. So on the left here, I have an image of Messier 51 taken in the U filter. So that's like a far blue filter in the Sloan Digital Sky Survey. And then on the right-hand side, I've got the translation of this image into a tactile image. So the way these images work is we take the brightest pixel, or the pixel that's closest to white, and we make that the highest point or the highest tactile feature of these images. We then take the blackest or the darkest pixel and we make that the lowest point of the image. So generally that will be the background of the image. It'll be sort of the base of the tactile image. And then we scale every other sort of shade of gray of pixel in between in terms of height. So we end up with basically a height map that represents the brightness of each part of this image. And so this really ends up being an analog of, I guess, the way you would look at this image. By running your fingertips across this image, you can feel the change in brightness, you can feel the shapes, you can feel all the details that you would be able to see, but you're doing it in a tactile way instead, but you're getting exactly the same information. So this is the basic idea that we came up with. And so Coleman wrote a plugin for a free 3D modeling program called Blender that basically allowed us to input any black and white image, like the one on the left, and create a tactile image like the one on the right that we could then 3D print or produce in sort of any other way that you can make a physical sort of 3D object. Okay, so with this idea, we started a pilot in 2016 with some funding from the Southeast Physics Network. This was a 6-month pilot run at half-time. And so because we had so little time to play around with, this really pushed us to be quite time efficient and to plan carefully. And we had to be quite focused. We didn't want to do anything too complicated. We wanted to take the idea that we'd had and see what we could do with it. So because we'd already identified the fact that we wanted to work with people who were blind and vision impaired, we saved ourselves a little bit of time there, but it also gave us the chance to find community members, so people with blindness and vision impairment in the local sort of Portsmouth community, as well as experts like qualified teachers for the vision impaired, who could give us feedback on our idea and help us develop it. So make sure that it was actually something that was going to be useful for the blind and vision impaired community. So we ran test sessions with local vision impaired support groups where we brought in a whole lot of different versions of these models. So we tried out all different kinds of heights of tactile features. We tried models with different resolutions of tactile features. We tried different sizes of models, and we got as much feedback from as many different people as we possibly could on which parameters suited them best, which parameters allowed them to get as much information from these models using their fingertips as they possibly could. We also ran community events where we sat down with vision impaired people and talked about these models and talked about the actual physics going on inside these galaxies to make them the shapes that they are. With the help of this community, we're also able to sort of adapt the way that we talked about the physics, the way we talked about these images, the way we talked about galaxies, to make it more appropriate for an audience that wasn't always relying on their vision to access the subject. So a really good example of this is we started off talking about the colors of galaxies. And so this is something that we tend to do. We talk about the, say, for example, the arms of spiral galaxies being blue and the cores of spiral galaxies being red. When we started doing this, though, a lot of the people we were speaking to were very quick to say, hey, color doesn't mean very much to me. Can you explain this in a different way that will be easier to understand? So it actually forced us to take a step back, to think about the way we were talking about these objects and to start modifying the way that we spoke about things. So when it came to color, it actually made a lot more sense to talk about the temperatures of the stars, the actual stellar populations that were causing the different parts of the galaxy to appear to be the colors that they were. So the cooler, redder stars in the core and the hotter, younger stars, or the stars that have maybe only just been born, in the arms of the galaxy. So it actually improved the way that we spoke about the science that we were trying to communicate. And again, it was all based on feedback from the blind and vision impaired community. Here I've got an image of the final 3D models, and you'll notice these look quite different from the original model that I showed you. And so these, the changes that have been made to this model are all based on feedback we got from sort of working with people with blindness and vision impairment. So you'll notice that we have the same tactile image, but there's a raised border around the edge. So one of the people we were working with said, hey, I'm getting a bit lost when I feel these models. I don't know how bright the bits that I'm feeling are, how dim the other bits that I'm feeling are. So the border is actually there as a way of, it's sort of like a yardstick. It's the same height as the brightest features in the tactile image. So people can bridge their hand between the edge and the tactile feature that they're feeling, and they'll get a sense for how high or how bright that part of the model is compared to that sort of brightest point that's represented by the border. You'll notice that we also have a nameplate attached to the top of the model. So that was another request made by somebody we tested the idea with, and they wanted a way to make sure that all of their models were sort of facing the same way. It was a quick way for them to identify what model they were feeling, and yeah, make sure that everything was sort of facing the same direction. You'll notice too, so I've got the front and the back of the model. On the back of the model, we've actually decided to put the image that the model's based on. And you might be asking yourselves, but why does that matter if people can't see? So the fact is, of course, that everybody with a vision impairment is unique. Some people will have a little bit of vision that they can use. Some people will have no vision at all. By putting the image that the 3D model is made from on the back of the model, it means that people who do have a little bit of vision that they can use, myself included, can look at that image and they can feel the tactile features corresponding to what they see on the other side. And so that just gives people another way of interacting with these models, using whatever combination of sight and touch works best for them. And it just means that the models are a little bit more versatile. And so all of these adaptations, all of these improvements to the model wouldn't have been possible if we hadn't have worked with the blind and vision impaired community from the very start of this project to make sure that what we were doing worked and that what we were doing was sort of going to work really well for that community. Okay. So by the end of the pilot, we knew enough about what we were doing to target a subgroup, I guess, of the blind and vision impaired community. So we decided to start focusing on students with blindness and vision impairment. And we had a much better idea of how long it was going to take us to produce resources. So, for example, these models take about 5 hours to 3D print. So you can imagine that making a lot of models is going to be quite time consuming. It's going to take a long time. Over the course of 2017, with lots of little bits of funding from the University of Portsmouth, from the STFC, and from the Southeast Physics Network, we were able to further develop these models to improve the way that we 3D printed these, but also to work on the way that we wanted to communicate sort of the science behind galaxies. And so to do this, we actually worked with some really wonderful vision impaired students from local primary and secondary schools around Portsmouth. We went in for multiple sessions with these students, and we talked to them about, again, about galaxies, about the physics going on inside galaxies that give galaxies their different appearances, their different shapes, how galaxies change over time, what they start off looking like, what they end up looking like, depending on what kind of lives they lead. And again, we were able to sort of improve the way we spoke about all of this with the help of these students. And these students helped us put together two lessons using our resources that were aimed at upper primary school students, and one lesson that was aimed at lower secondary school. And so the way these lessons work is they start off with really simple concepts and they build them up. So they build up the idea of distances and shapes and all kinds of other things like that. So with the primary school students, we'd start off talking about the solar system. So using really common household objects, so things like tennis balls, ping pong balls, peppercorns, mustard seeds, and even beach balls, we'd be able to get the ideas across about the different scales in our solar system. So how big the planets and the sun are compared to each other. So in this scale, the sun would be a beach ball and the Earth would be a peppercorn. And you can imagine just how powerful that analogy is, how you can get a real sense of the scale difference between the sun and the Earth just using those common objects. We also do activities where we get students to basically map out the solar system, so the distances separating the planets, using tactile rhinestone stickers on a long strip of paper. So just using simple exercises like this, we're able to build up concepts relating to sizes and scales that are maybe a little bit more relatable than the massive scales and the massive distances we're talking about when we discuss galaxies. But using these ideas of scale and distance, we can then start to talk about our place in the Milky Way. So we can use tactile images of the night sky to talk about stars, where these stars are situated in relation to us, how they make up the larger Milky Way. And then we can get students to actually build their own simple model of the Milky Way using a CD and some Play-Doh. And the idea here is that they'll get a sense of the basic shapes that make up a spiral galaxy, that make up something like our Milky Way. So they can build bulges, they can build spiral arms, they can feel the thin disk represented by the CD. We can then move on to talk about galaxies. And so we've settled on 10 different galaxies. They're all quite unique in terms of morphology. They all have a different story to tell. And we could use all of these galaxies to basically talk about what makes galaxies different shapes, what gives them their different appearances, what gives them their different colors, and so how they change over time. To talk about color, though, we had to be a little bit tricky. So obviously, we're all used to looking at false color images of galaxies that have got all of that color presented at once. It's worth remembering, though, that when we image galaxies, we do it with telescope filters that isolate particular wavelengths of light. So we will focus on the blue wavelengths or the red wavelengths or the green wavelengths, and then we stack those together to make full color images. So it was actually relatively easy to discuss color in this way. So we basically produced for each galaxy 2 different images, one that uses a red filter, and the other that uses a blue filter. And you can see in the example here that this shows a very different version of the same galaxy. It really highlights the different features that are particular colors in these objects. So we're able to discuss color in this way. And again, just taking a step back, doing things this way actually makes things a lot clearer for people because we're talking about the physics. We're talking about the individual colors rather than mixing everything together. We're able to provide a much clearer picture of what's going on in these galaxies. Okay. So we'd worked with these schools. We developed all of these workshops that we wanted to deliver. And we realized that we had something that was going to be really useful for students with blindness or vision impairment across the UK. So we wanted to try and get our resources out to as many people as we possibly could. In 2018, so Jen Gupta led an application for an STFC Nucleus Award, and we were successful in that application. And so using the funding from that award, we aim to create and deliver inclusive workshops to upper primary and lower secondary school pupils. We wanted to train others to use our resources, so to deliver our resources to their local blind and vision impaired student communities. We wanted to create physical resource kits that we could send out to these people that we trained so that they could basically just start using those resources as quickly as possible. And we also wanted to share all of our resources digitally, so anybody who was capable of 3D printing these resources themselves would be able to do that. And anybody internationally who wanted to take up the resources and use them as well would be able to do that. So to do this, in 2019, we ran 5 presenter training workshops. So these were day-long workshops. They were in Edinburgh, London, Portsmouth, Birmingham, and Manchester, and they were attended by a total of 66 people. This was a mixture of science museum operators, qualified teachers of the vision impaired, outreach officers, researchers, and just interested members of the general public. And so we spent these workshops showing people how to use our resources, building people's confidence in the idea of working with blind and vision impaired people, because there was a lot of trepidation from people. People were worried they were going to say something offensive, they were going to say the wrong thing, they were going to confuse people, give people a bad experience. So a lot of the workshop was us, I guess, demonstrating the best way to sort of do that. And also showing that, yeah, if you try, you're not really going to insult somebody. If you're trying to help somebody access something that's traditionally difficult for them to access, it's generally going to be a good experience. We also produced 20 resource kits, which we then sent out to a select number of these people that we trained so that they could start delivering the resources. And so these workshops were a lot of fun. You can see this is the one that we held in London at the Royal Astronomical Society. There's a lot going on in this picture. On the left-hand side, we have a totally blind woman who runs a theatre company. So she was really intrigued by the idea of the Tactile Universe, and she wanted to come along and learn more about it. She is actually talking to all the other people around her about how she is perceiving these models, so what she's getting out of them by touching them, what kinds of features she's feeling. And this small group down the end of the table are working together to develop the language that they can use to talk about the features that they're feeling. So yeah, these workshops are really, really fun. They're a lot of fun to run. In terms of these models, to speed up the production of these models a little bit, just for this part of the project, we actually created models using resin. So we cast models out of liquid resin. We actually embedded the images inside these models. So Coleman spent months basically making 400 galaxy images to make up these 20 resource kits. And on the right-hand side, you can see we're loading the resource kits into a van. The Outreach and Public Engagement Officer at the ICG at the time, Cordy Scott, basically drove all of those resource kits to all the different people around the UK to deliver those to them. And just before the pandemic set in, we were actually seeing some of these groups with our resources beginning to deliver to their local vision impaired community. So they'd spent some time getting in touch, finding local schools that had vision impaired students, working out who they could deliver to, and they were starting to deliver their first workshops. And you can see from these tweets that the experiences were really positive. The students were getting a lot out of this. They were really enjoying the resources. They were enjoying the fact that the resources were directed at them, something that they could access. We were beginning to see some really nice messages of sort of inspiration from these vision impaired students as well. And so I've got 3 quotes here from our interactions with school students as well. Just to summarize these, though, I know there's a lot of text on the screen. We got some really positive feedback from students. So they were more inspired by science. They wanted to pursue science as a course of study as they moved forward. They were really happy that science had been made accessible to them through this project. We also got some really nice quotes from the vision impaired, qualified teachers for the vision impaired that we work with as well. So them basically observing their students. They were noticing that a lot of their students were getting better at critical thinking. They were getting better at asking questions. They were getting better at socializing with the rest of their classrooms. And so it's worth noting that in this context, a lot of the students that we work with are vision impaired, but they're actually part of mainstream classrooms. So there'll maybe be one student with a vision impairment in an entire class made up of students, mostly with perfectly good vision. And so by running these workshops with those classes, so with students with perfect vision as well as the students with vision impairments, getting everybody to work together on the same thing at the same time, using these accessible resources, it was actually allowing the vision impaired students to work alongside their sighted peers using the same resources. It basically put everybody on the same level, the same footing. It also got a lot of the sighted students thinking about how the vision impaired students could access things. So it got them sort of thinking about their vision impaired peers as well. So lots of really positive experiences, lots of really positive feedback. It's nice to see that these resources are having the impact that we hope that they would, and that they are inspiring young people and changing the way that they think about STEM subjects. Okay. So as part of the Nucleus Award as well, we were able to share our resources online. So this included the files to 3D print our models, Coleman's code, so that anybody can use to take any black and white image and make a tactile image out of that really easily. We were also able to share the lesson plans and the sort of scripts that contain the basic things you would want to say if you were to run these workshops with a classroom. We also provided a lot of supporting documentation, everything from sort of best practice for interacting with vision impaired students to how to 3D print these models. So the kinds of pitfalls that we ran into when we were producing these models, to how to make the model. So really detailed guides on every aspect of the project. Really soon as well, we're going to be adding some instructional videos that presenters will be able to look at to help them learn how to use these resources with their local communities as well. And we're hoping that this will allow people who didn't attend these training workshops that we ran, people internationally will be able to use these resources a little bit more easily. Okay. And we've already started to see groups around the world picking up these resources quite randomly, actually, to use them. So on the right, I've got a tweet from a group at the University of Toronto who've started printing our resources and using them as part of their stargazing evenings. So that's really exciting to see that people are actually finding these resources and that they're seeing the value in them and using them. I've included this as well, just because. So Jenny tweeted about this earlier on in the week. Jenny Carter is a researcher at the University of Leicester. She's been in communication with us and has been using our 3D modeling code basically to make tactile images relating to her research, which involves the image spacecraft and auroral boundary data. So it's really exciting to see other people taking this code and starting to use it to make images of things that aren't galaxies as well. So that's really exciting. So I talked about how we've been, one of our aims, I guess, at the start I talked about was that we really want to be helping other people improve the way that they are communicating their science, make their science more accessible. So we've had involvement with a few international projects. On the left, I've got the logo for the Astro BVI group. So we shared our resources and some of our lesson plans with them. They've taken those, made roughly 100 resource kits and sent them out to countries all across South America, as well as Spain and Nepal. And so they're helping us get the resources out to audiences we otherwise wouldn't have been able to reach. We've also been lending our expertise to the iData group in the US, who are making a fully vision impaired accessible observing interface for a robotic telescope network. So that's really exciting as well. We've also worked with museums. So here I've got a picture of the Gaia Milky Way, the panoramic view basically of what we'd see if we could see the entire Milky Way from the Earth. And so we helped the Museum for Life in Newcastle make a massive 1.7 by 0.4 meter tactile image of that people can come into the museum and feel. And the idea, of course, here is that anybody, not just people with vision impairments, will get something out of this image. They'll get a slightly different experience than they would if they were just to look at the visible image of this. We've also been able to talk to people about how they can make their work more accessible at conferences, both nationally and internationally. So on the left, the CAP conference that was held in Japan back in 2018, we were able to use our resources as an example of how science can be communicated more effectively and more accessibly. And on the right is an example of a presentation that I put together on how to make accessible presentations and a lot of the pitfalls that we as academics and researchers and public engagement people make when we present, the kinds of things that can make our presentations really, really inaccessible to different audiences. We've also started to work with other researchers around the UK. So here I've got an example of some 3D models that we developed for a British Science Festival show that was led by Chris Harrison, who was based at the ESO, but it's now based in Newcastle. So Chris developed all of these wonderful sounds that represented various phenomena in space. So some were based on real data, some were sort of slightly more abstract representations of things like the stars appearing as the sun goes down in the night sky. So Chris and I were able to develop a show that used just these tactile models and just Chris's sounds and basically took people on a tour of the universe. And this was attended by sighted people and vision impaired people. We blindfolded people so that everybody was having the same experience. And overall, the feedback from this was really good. Chris has now gone on to do even more work. He's currently developing a planetarium show that uses sonification, so astronomy data as sound, that is also going to include visuals, but will be completely accessible to people with vision impairments. So it's a really wonderful initiative that Chris is working on. The work he's doing is quite fantastic. We've also started to get a little bit more mainstream recognition as well. So last year, in 2020, we were featured in one of the episodes of The Sky at Night, which was something I've basically dreamed of since I was a little kid. So that was really exciting. Slightly more randomly, one of our models, so a tactile image that we made of the M87 black hole image taken by the New Horizons group, was actually presented to the King of the Netherlands as part of an IAU gala that was celebrating the work that the Netherlands has been involved in astronomy over the last 100 years. So yeah, we really are seeing our models, projects that we've helped with, other things like that popping up in a lot of different places. And it's just really, really exciting to see so many groups taking on the message of accessibility. Okay, so before I finish up, I thought it'd be important to tell you what we're planning on doing next, what our next steps are. So obviously the pandemic has been a little bit difficult. With a project that relies so heavily on face-to-face interactions and tactile models, it hasn't been particularly safe for us to operate as we normally would. So we've been quite limited in the way we've been able to deliver the project over the course of the pandemic. At the start of the pandemic, though, we applied for an STFC Legacy Award to basically continue the work that we were doing. And we were, again, successful in that application. What we're hoping to be able to do is maintain this network of people that we've trained to help them deliver our resources as effectively as they possibly can. So what we're going to be hoping to do is hold virtual meetings, so semi-regular virtual meetings, basically allowing everyone to share their experiences. So as these groups start to deliver the resources, we want them to be able to talk to each other about what's worked and what hasn't. Maybe some of the new ways they've come up with for describing things that some of us might not have thought of. We also want to provide a shared evaluation framework. We know that evaluation is really important. Getting as much feedback from the people who use these resources is really important for making sure that we can improve the resources as we move forward. We want to know what works, what doesn't work. The other important thing is that because we have workshops that target different age groups, what we're hoping is we'll eventually see people who've interacted with our resources at a primary school level, but then have moved on to interact with our resources at a secondary school level as well. What we're hoping is that we're going to be able to track some change in their aspirations, in their confidence in science, and their confidence in their ability to do science. So there's some really exciting stuff that we're going to be able to collect through this evaluation framework. We're also hoping to develop some shared and evolving FAQs that anybody can sort of change or edit, again, based on their experiences, things that they do that work, things that they do that don't work. General guidelines that people will be able to use to make them feel more confident with the idea of teaching and working with people with blindness and vision impairment. The other thing that we're hoping, or that we're going to do over the next 2 years with this Legacy Award funding, is that we're going to develop multisensory approaches to communicating gravitational wave science. And we want to make workshops that will target students in upper secondary school. So again, there'll be that other age group that we'll be able to target with this stuff. Once we've developed those resources, we're going to train members from LIGO research groups around the country or around the UK, so that they can then deliver these resources as part of their public engagement programs. And we're also going to hope through this that we'll be able to expand the reach and the membership of this network of presenters, both nationally and internationally. And I just wanted to really quickly show you something that we've been working on. So this is our sort of really, really early take on how we could maybe start communicating the idea of gravitational waves moving outwards from two gravitational masses that are merging together. And so one of our PhD students, Simone, has basically made this black and white image. So he's modeled a sine curve that changes in amplitude as it moves out from these sources. And again, we haven't actually modeled this shape per se. We've just used this image in Coleman's code to make this surface that represents these ripples. And we're hoping that using something like this, we're going to be able to communicate these ideas. The great thing about gravitational waves as well is that there's a lot of scope for us to include sound alongside these tactile resources. So we're hoping by the end of these 2 years, we're going to have resources that use sound, touch, and vision. It will give people multiple ways of accessing this research, but it'll also allow for people to use their strengths, whatever they feel more comfortable using, whichever sense is the best for them. Okay, and finally, I thought I'd leave you with some lessons that we've learned along the way. So working with underserved communities like people with vision impairments can be really challenging to begin with. It can be quite difficult. We definitely found that convincing people who'd been told their entire lives that they couldn't do astronomy, that astronomy was something they couldn't access, that it was going to be too difficult for them, it actually made it quite difficult for us to engage with these people to begin with, because they had this ingrained idea that it was going to be too hard, that they weren't going to be able to do it. But when we actually started to work out ways that we could communicate with their help, it was actually really rewarding for everybody. It was rewarding for us. It improved the way that we talked about our science. And it was rewarding for these people because we were opening up a topic that they'd maybe been interested in, but they hadn't really been able to access. I'd also say not to be afraid to use the expertise and the experiences of the community that you want to work with. Nobody knows what they need better than somebody with a vision impairment. Everybody's going to be slightly unique in the way that they've adapted, the way that they've learned to cope, the way that they've learned to get around and just to do things and live their life. And so getting their experiences, working it into the way that you want to deliver your project is really, really crucial. And it'll often have some really unforeseen and quite surprising consequences. Our models are a really good example of this. They have so many additional features that they wouldn't have had if we hadn't have gotten the feedback from the vision impaired community. Lastly, it's really important to note that accessibility ultimately benefits everybody. So if we can improve the way that we communicate our science, if we can improve the way that we talk about things, if we can improve the way that we can allow people to access things, it's not just going to help the people that we originally target, it's going to help absolutely everybody. And we've definitely seen that with the Tactile Universe. We get so much feedback from people who don't even have a vision impairment, who touch these models and think that it's a wonderful experience. They love being able to access astronomy in a different way. They often feel details with their fingertips that they wouldn't have been able to see with their eyes. So the real message is that accessibility helps everyone. Even if you start off just trying to work with a really specific group of people, you will ultimately make something that will benefit absolutely everybody. Okay. And finally, there are lots of different ways that you can access our project and get in touch with us. We have an email address, tactileuniverse@gmail.com, that you can email if you want to talk to us about making what you're doing more accessible. If you want to try and make your own 3D models and you're having trouble and you need some pointers, you can get in touch with us as well. We also have a website where we host all of our models and host our blog posts, which describe how to do everything. That's www.tactileuniverse.org. And we also have a Twitter account, which I need to get a little bit better at posting stuff on, but you can find us at Tactile Universe on Twitter. And again, thank you so much for the opportunity to talk today. It's been an absolute pleasure, and I'm more than happy to take questions now.
Thank you very much. That was a fantastic talk. And I think, yeah, your point about accessibility benefits everyone. We need to really keep that in mind more. This shouldn't be an extra thing that we're doing. We shouldn't consider it an extra thing. We should just be doing it. So we're getting lots of questions. So I'll start with those. So a question from Robert Massey. He asks, beyond your excellent work, what more do you think the astronomy community should be doing to encourage vision impaired people to pursue study and careers in our sector?
So I think, obviously talking to people when they're young is a really good idea. So we have all kinds of really great reports like the Aspires report that show that engaging with students when they're younger, we can be much more successful in building people's science capital. So their general view of science, how useful they think science is, how accessible they think science is, whether they see themselves as scientists. So I think showing people at a young age that subjects like astronomy can be accessible, that sometimes we have to think outside the box, we have to do things in slightly unusual ways, but also not being dismissive. So I'm quite lucky, I think, in that as a vision impaired person growing up with an interest in space, nobody ever said, Nick, this is going to be too hard for you, you shouldn't do it. But we definitely, especially when talking to slightly older people, we do hear stories of them being literally taken out of classrooms and sort of told, no, you can't do this, it's going to be too hard for you. That's definitely not happening anywhere near as much now. So a lot of the younger people with vision impairments who are studying right now have a lot more opportunities. They have much more positive experiences. But I think, yeah, we're the experts here in terms of communicating our topics. But if we can find accessible ways to do that, then we're going to be able to show people and sort of inspire people from a young age. I think one of the biggest issues, though, is, I guess, in terms of academia, academia can still be quite inaccessible for people with disabilities. So the kinds of workloads, the amount that we're sort of expected to work to actually be successful as academics, the kinds of reading that we have to keep up with to stay sort of abreast of topics that we want to research can be quite fatiguing for people with disabilities as well. So that's all sort of things that we have to consider. One thing I will say, though, is that there are more and more and more initiatives popping up around the world that are looking at ways to make astronomy more accessible. So there are lots of projects looking at tactile resources. There are lots of projects in particular who are looking at sonification as a way of communicating astronomy, but also of doing some really, really good research as well. So sonification is a way of doing research. There's actually an upcoming meeting called the Audible Universe that's going to be run in Leiden later this year that's going to bring a lot of those groups around the world together, get everybody talking, start to look at ways that we can make research more accessible in general.
Fantastic. I'm going to use my chair's prerogative to ask a follow-up question on that. So about sonification, do you find that it's whether, say, making a 3D model or using sound, that one tends to work better than the other? Does it depend on the data or the person, maybe, or is it just?
Yeah, so there are lots of factors. So it does depend on the data. So obviously, I think images and spatial data lend themselves a lot better to tactile graphics. There are lots of efforts to represent images using sonification. I think those work, but they can be a little bit complicated. It can be a little difficult to interpret at first. I think where sonification has a lot of its strengths is where we're looking at signals, where we're looking at things that are moving as well. So a lot of the stuff Chris, for example, is working on, he's representing the orbits of the planets in the solar system using sonification. So there's this beautiful sort of sense of things moving around you. And definitely communicating spatial stuff like that, especially people who've been blind their entire life, can be quite difficult. But using sound actually is a really, really powerful way of doing that. But yeah, it's so dependent on the person as well. So one really famous vision impaired astronomer, so Wanda Diaz-Merced, so she primarily works with sonification. The main reason for that is because so her blindness has been caused by diabetes. So she can't actually do a lot tactilely because her fingertips hurt so much because of her illness. So we've showed her our tactile resources. She's been able to feel them a little bit, but her ability to actually use tactile stuff is quite limited by her illness. So for her, sonification is a much better way of doing things. So yeah, it depends on the individual as well. Some people are just going to be much better with sound than they are with tactile. Some people are going to be much better with tactile than they are with sound. Some people are going to be able to use a little bit of vision to augment everything as well. So it really is dependent on the individual. I guess the message is, by presenting things in as many different modes as we possibly can, we give people the option to access topics in whatever way suits them the best.
Brilliant, thank you. So we're getting a lot of questions. So from Megan Argo, so it's fantastic work, Nick. Do you have, or are you working on a set of guidelines that the rest of us could use to help us be more inclusive in the way we talk about what we do when we talk to the public? So is that in the guidelines you mentioned towards the end?
Yeah, so that's something that we're working on. Again, so much of that ends up being context specific. A lot of the stuff we came up with, we wouldn't have come up with ourselves. So it was more that we started talking about things and somebody piped up and said, hey, that doesn't make sense to me. Can you explain it in a different way? So I think, so we've cited a lot of the examples that we have of the way we describe things in the sort of workshop scripts that we've written. Yeah, I guess that is probably something we do need to do at some stage, is sit down and actually write out some slightly more broad guidelines on all of this as well. Yeah, that's a really good point. So yeah,
I think it's really interesting, like what you were saying about people who have very little or no experience of color, explaining what colors mean is not helpful, and it made you think about the science more and how to communicate. Yeah. I think that's
no, absolutely, and it did improve the way that we talked about things. But also, so all kinds of weird things as well. Like when we started talking about blue as hot stars, red as cold stars, because of the way a lot of these blind and vision impaired people have been taught. Also, just regular school kids as well. They said, but why are hot taps? Why are hot taps red and why are cold taps blue then? So there was this whole other sort of side discussion where we had to sort of unpick this preconception and sort of reverse this idea that blue was hot and red was cold. So yeah, you don't get any of this stuff unless you actually communicate, if you don't have this back and forth.
To be fair, that confused me like well into my 20s.
I think it confuses us all.
So this is a cool one. So following on from the colors like red and blue not meaning much, and the temperature is a better analogy, would it be possible to locally heat or cool part of the models so people would feel that difference in temperature?
Yeah, so that's actually something it's gone in our list of things we'd love to do if we ever have time. So yeah, you could run wires through the tactile model. And you could imagine heating and cooling different elements, or you could even have fluid, so tiny pipes running through the inside of the model, where you potentially, again, heated water, cooled water, did all kinds of things like that. So I think one thing we learned very quickly with this project is that we had a really cool idea, and there were lots of amazing things we could do, but we had to be focused. Otherwise, we were just going to get bogged down in all of these amazing ideas. What we do hope, though, is that because we've made everything available for free, so we've shared our resources, we've shared these models, we've shared the code to make the models, we don't want anyone to have to pay for this stuff. We want people to be able to pick this stuff up and just do whatever they want to with it, make their own models. We do hope that somebody is going to sort of go, hey, wouldn't it be cool if we could do this? And they go away and work this out themselves. But yeah, we have a massive box of cool ideas that we just haven't had a chance to get around to. Maybe one day.
I could see it's very easy to go down a rabbit hole on this and just So another anonymous question. Very inspiring work. You made a brief comment that we often make presentations with obvious pitfalls which make them rapidly inaccessible. Could you give some examples of these pitfalls we could improve?
So one of the biggest things is, and I actually realized I failed to do this during this presentation a couple of times. I'll mark that one up to nerves. If you ever have an image on screen, make sure you describe it. You don't have to describe it in ridiculous amounts of detail. You just need to give a brief summary. So make sure, I think that the biggest thing is, even if you have a fully sighted audience, if you've got a lot of stuff going on in your slides, it can be difficult for the audience to know where they need to be focusing at any given time. So if you have an image, if that image is important, make sure you draw the audience's attention to that verbally when you talk about that image. So make sure they know what they're supposed to be looking at. Make sure they know what key points they're meant to be getting from that image. And I think that's particularly true when you put plots up. So plots will often be quite complicated. You'll be getting a lot of information across just with one image. Take the time to explain what parts of that plot are actually important, what parts you really want the audience to take away. Don't assume your audience knows what bit of that plot they should be looking at. You probably noticed as well that most of my slides had not a ridiculous amount of text on them. That's another good thing as well. If you have an audience member who can't hear what you're saying, but is just going to be reading the information off your slides, you want to make sure that they're able to keep up with you as you're going along. So not having ridiculous amounts of text is a really good thing. Also, you probably will notice my slides are quite high contrast. So again, that just makes it a little bit easier for people to pick out the text, pick out the pictures, pick out whatever information they need to. So yeah, those are just the sort of basic things, I guess.
Thank you. So we'll got that. It's a very quick question from Saheb Mandhai. Really interesting work, Nick. What's the name of the Blender plugin for the black and white to 3D model? Is that linked on the website that we have up now?
Yeah, so it should be linked on the website. I think it's hosted on GitHub. So Coleman has done a really good job of updating that every time Blender gets updated as well. Because yeah, Blender's gone through some pretty serious changes over the last couple of years, and it's basically broken our code every single time. So yeah, I think on our website there's the most recent blog post should be a rundown of how to use that plugin in the current version of Blender. But yeah, you can access the code through our website.
Cool. So a question from Chloe Sumner. Sorry. You mentioned reading, but in the context of like how to for practicing scientists, I guess the word is. She's wondering if scientific papers are accessible to visually impaired people or others like dyslexic people. I can tell you no.
Yeah.
Can we do anything to publish in a way to remove these barriers to entry?
Yeah. So there are. It's a bit tricky. So some papers definitely are getting more accessible. So they're much more screen reader friendly. Definitely in my case, I tend to just blow everything up really, really big so I can see it on my screen. What does get a bit inaccessible is when people produce plots that don't work well in black and white, or plots that are just okay. So especially if you're showing a lot of different data sets alongside each other, a lot of people make the mistake of not making their data points distinct from one another. So as somebody with low vision, that can be really, really difficult for me to sort of look at that plot and actually interpret the different data sets. These are all things that we can think about when we make our plots. We can make our axis labels bigger. We can make sure that our points are really, really different colors. We can make sure that we've used really distinct symbols for different data points. There's lots of little things like that. There are journals that are starting to think a lot more about accessibility, so how they can make their papers easier for things like screen readers to read. Definitely equations are still something that can be a little bit difficult, but again, there are people working on LaTeX plugins that actually produce PDFs with maths that is readable by screen readers, that actually the screen reader will read that equation in a way that actually makes sense, that you can interpret. Whereas if it hasn't been optimized for that, a screen reader will just read that equation as absolute gibberish. And so you miss out on a whole chunk of the science in the paper if you can't access that equation.
Yeah,
so
like
it's a bit of a mixed bag, I think, is the message.
I think the simplest thing you can do for plots, print your paper in black and white. Can you still see the differences? If you can't, then nobody else can.
Yep.
So
and make things a bit smaller as well, and make sure you can still read all of your axis labels and everything like that. Because yeah, oftentimes we end up with absolutely teensy weensy axis labels that nobody can actually see. So
yeah. So we have an anonymous question here. Do you think much of the work and ideas that have come out of the Tactile Universe are transferable to other areas of physics and science where visuals are often used in the classroom?
Yeah, so we have seen a few other groups. So there have been some biologists who've taken our code and used them to make images of slide plates of sort of biological type things. So yeah, there are extensions of, I guess, our work to that as well. I would argue that astronomy is probably one of the most visual sciences out there. You might disagree with me there. But yeah, as I said, I mean, with astronomy, there are so many reasons why we shouldn't necessarily be doing things in quite a visual way as we are. This whole idea of augmented vision, the fact that we have to rely on so many artificial ways of enhancing what we see to actually see it properly. I also would argue that there are going to be a lot of strengths in astronomy in particular in using things like sonification. So, for example, picking signal out of really noisy data is going to be so much easier in a lot of cases using sound than it would be just trying to pick that out with our eyes. So, yeah, but I think, yeah, there are definitely applications for this to other sciences as well.
Awesome. So another one, if visually impaired people become more attuned to other senses, does translating data from visual representation into other experiences produce breakthroughs in analysis too?
I mean, we're not seeing this yet just because it isn't commonplace enough. But I'm sure, I mean, I think, so again, Wanda is a really, really good example of this. So the work she's able to do with sonification is pretty amazing. So the stuff she's able to detect by turning her data into sound is really quite spectacular. And I think, again, in some cases, I think there are examples where people who have a more attuned sense of hearing. So again, you've got to remember with a vision impairment, with any disability, it's not that our hearing is better or that our sense of touch is better. It's just that we've had to rely on those other senses more. So we become more sensitive, I guess, is a better way of thinking about it. And so I know, I mean, an example I can cite in my own experience is images of galaxies where we have lots of foreground stars hidden amongst the actual sort of I guess the main galaxy. So foreground stars hidden amongst the arms, hidden amongst the bulge, or kinds of things like that. You can actually feel those really, really clearly in a tactile model because they feel like pins. It's actually really unpleasant to run your hand over the top of a foreground star. And if you're bumping into those, where they might be hidden amongst all the rest of the light, that's sort of the starlight coming from that galaxy, I guess that's just an example of where somebody with a slightly more sensitive sense of touch, I guess, will pick up stuff that maybe you wouldn't pick up with your eyes necessarily. So
that's cool. So I was wondering as well, like with the models, so you do you have to play around a lot with things like the scaling, like to make it log scaling or whatever, to make those features stand out beforehand? Or?
Yeah, so I mean, we do actually, the nice thing about the way these models work is we do basically just use log scaling. So we process these images the same way you would if you were going to present them visually, but then that actually translates really nicely to a tactile feel as well. So yeah, all of our galaxy images are log scaled. Well, there's one or two cases where we've had to clean up some of the noise a little bit, but as much as possible, we try to leave the images as raw as we can, because if they have satellite trails, if they have lots of noise, if there's lots of foreground stars, basically, if people detect that and then they want to know what's going on, it gives us an extra chance to talk about something. So it sort of opens up extra avenues of questioning, extra ways of discussing sort of what's going on in these images. Yeah, so...
So we have a question from Edward Gomez. You've mentioned you're working with a group to make robotic telescope use accessible. Are you thinking of adding this into the Tactile Universe?
Yeah, I think that is something that we would like to do eventually. So, I mean, you can obviously imagine that if you have an image that you can listen to. So again, this is a group who've they've made all of the interface accessible, but they've also provided a way to listen to the image that your telescope has taken and sort of get a sense of what kind of object it is, whether there's lots of noise. So the way they've done this is they sort of scan line by line across the image and they play tones based on where the pixels that are bright are, I guess. So you can imagine too then moving on and actually 3D printing the image that you've taken. Yeah, so this is something we've looked at a little bit. We've shared our code with the iData group. I know that we also worked with the LCO observatory to basically take our own data with some vision impaired students and turn that into tactile images as well. So it's definitely something that we want to do a little bit more work on in the future. It's just going to be a matter of finding the time to do that.
Cool. So we've got about 1 minute left, so I'll just try and get one more question in from Ronan Laker. How did you choose which galaxies to make into models?
So I guess we wanted a really good representation of different morphological types because we sort of wanted to be able to tell this story about how galaxies change over time, what causes different changes, how galaxies can merge to form things like ellipticals, all this stuff. So we looked at mostly nearby galaxies, I guess, galaxies that were quite bright, had a lot of detail. So a lot of our galaxies are Messier objects just because they're relatively well known, they're very clear. They translated really nicely into tactile images. So yeah, the long and the short of it is, yeah, we mostly did choose relatively nearby, relatively bright, relatively well-resolved images. But yeah, we really wanted this representation of different galaxy types. We also wanted enough different galaxy types that we could get students to do things like sorting exercises. So basically making up their own morphological classifications. So for the vision impaired students, oftentimes this will be the smooth galaxies versus the bumpy, lumpy galaxies, which actually translates really nicely into spirals versus ellipticals and other things like that. So
that's super. So like Galaxy Zoo, but classifying it over what you can feel rather than...
Absolutely. And that was a big inspiration for that sort of aspect of the project as well.
That's super cool. So we're at the hour now. So I'd just like to thank Nick again for a really fantastic talk. And hopefully we can all take some of these things back with us and make sure we think more about how to make our science accessible to everyone. So thank you again, Nick.
Thank you so much. It's been an absolute pleasure.
Thank you.